Good afternoon, everyone, and welcome to What's New with Connectivity and Control Services. My name is Jared, Senior Product Manager for AWS IoT Core, and with me is Shane, Senior Product Manager for AWS IoT Device Management. And we're really excited to be here today to recap some of the major launches from 2019. So to start out, I'd just like to give everyone a quick refresher on how the connectivity and control services fit into the greater suite of AWS IoT services. So connectivity and control is comprised of three individual services: AWS IoT Core, AWS IoT Device Defender, and AWS IoT Device Management. And these services are really designed to help you manage interactions with your devices, whether that's collecting telemetry data, issuing command and control messages, doing device lifecycle management, things like OTA updates, monitoring the status of your fleet, or monitoring the security of your fleet and maintaining security best practices. And in 2019, we actually had exciting new feature launches across each of these three services. So to start out, I'll be going over some of the new features for AWS IoT Core, and then I'll pass it over to my partner Shane to talk a little bit about device management and device defender. So IoT Core itself is comprised of 6 components. We have an identity component for managing fine-grained access control, a device gateway component for managing device connectivity, a message broker component, which is a fully managed pub/sub broker that implements the MQTT 3.1.1 protocol, a rules engine component for managing interfaces with your backend application, so sending device data to your backend application, a thing shadow component for persistent state storage and manipulating the state of your devices, and a thing registry for managing device metadata and interacting with the device management service. So in 2019, we had 7 major feature launches across multiple of these components. And these feature launches can broadly be kind of classified into 2 main categories. The first 5 deal with making it simpler for you to connect your devices to the cloud. And the last 2 deal more with helping you get device data from your devices into your backend application. And I would like to just quickly point out, you'll see a number of the features here are listed as being in beta. All of these betas are public betas, which means that anyone can use them. They're just only available in the US East 1 North Virginia region, and may be subject to some minor API changes until they are put into general availability. So the first feature I'd like to talk about is fleet provisioning. And fleet provisioning enables you to use a trust anchor to uniquely configure a generic device the first time that it connects to AWS IoT Core. And what this means is you can take a device that does not have unique digital credentials, and you can get it configured with unique credentials, so in this case, an X509 certificate and associated keys, and have that activated for use in IoT Core. Also attach an IoT policy, which allows it to perform various operations in IoT Core, and as well optionally configure a thing in the registry for that device. And fleet provisioning makes this possible through 2 new workflows. So in the first workflow, called Trusted Bootstrap Identity, your trust anchor is actually a common device certificate that's used across all your devices. So this is really designed for the use case where, let's say you are a device manufacturer, and you have a standard firmware image that you would like to use for all of your devices, and you don't want to have to go through the complications of configuring unique credentials for each device at manufacture time. What you can do is provision your device with a generic bootstrap certificate that you register with IoT Core. And the first time your devices connect, they will connect to the fleet provisioning APIs and use this common bootstrap identity with some unique identifying characteristic like a serial number. And in fleet provisioning, your template will enable you to decide whether you want to provision unique credentials for that device and get it all set up and configured to talk to IoT Core. And the second workflow that fleet provisioning makes possible is what's called the trusted user workflow. So in this case, your trust anchor, instead of being a common certificate, is actually a well-known mobile app. So this is for the case where you have a smartphone device, or sorry, smart home device that may be paired with a mobile companion app for configuration. So upon configuration, as part of the user workflow setting up the device, the mobile app can also be configured to talk to the fleet provisioning APIs, receive the unique credentials for the device, and then pass them directly to the device over the local network. Whichever workflow you choose, the end state of the device is the same. The device will be set up with a unique X509 certificate with associated keys, an IoT policy that allows it to access IoT Core, and optionally, you can configure a thing in the device registry. So fleet provisioning makes this possible through 3 new components. The first is the provisioning template. And here's actually where you define the initial trust criteria for the device, so what you will use to uniquely identify the device, like, for instance, maybe a serial number. As well, you define what sort of policy the device should receive if it's activated, and also optionally define how it should be set up in the thing registry if you choose to do so. The second component is an updated IoT device SDK. So this is just additional libraries for our standard device SDKs that enable devices to directly communicate with the fleet provisioning APIs in the case that you're using the first workflow, the trusted bootstrap identity. And the third and final component is updated mobile SDKs. So this is the same thing, but for the second workflow, the trusted user workflow. So you would add this SDK to your mobile companion app, and then your mobile companion app would be able to serve as a trusted proxy for your device to receive the device credentials and pass them on to the end device. So the second feature that I would like to talk about is also related to device provisioning, and this is called multi-account registration. And this is used in the case where you are bringing your own device certificates. So you already have unique certificates prepared for your device that you are bringing and wanting to register in IoT Core. And what we enable you to do with multi-account registration is actually register the same certificate in multiple AWS accounts. And this is really, really advantageous for customers who may have multiple pre-production environments that are operating in different accounts. So you can easily imagine a case where you have a test environment, a QA environment, and a production environment. And your devices are going through some qualification process where you start them off in test, they pass some tests, you move them to QA, and then give them the final go-ahead to move on to the production environment. And you don't want to have to provision new credentials for your device every time you promote them to a new environment. So this feature enables you to register the same set of credentials in all 3 accounts. And you do this by having the device send the TLS extension server name indication with the account that is trying to reach its fully qualified domain name in the SNI field when it connects. And that's how we determine which account the device should actually be connected to. As a side benefit, multi-account registration also enables you to register your own certificates without having to supply the CA certificate that signed the device certificate every time you're registering the new certificates. So the third feature I'd like to talk about is configurable endpoints. And whereas the first 2 dealt more with how you provision credentials for your device, this feature really deals with configuring how your devices connect to AWS IoT. And we do this by enabling you to customize the behavior of your IoT Core endpoints. This is done through a new IoT resource type called a domain configuration. And each domain configuration corresponds to a unique, fully qualified domain name, whether that's an Amazon-issued domain name or a custom domain. And as we'll see in a second, domain configurations enable you to set up custom domains on your endpoints, as well as attach custom authorizers to use your own authentication and authorization schemes. Also, in the near future, you'll be able to do some TLS configuration on your endpoints. And what's meant by this is you'll be able to control things like minimum TLS version that should be allowed on your endpoints, or what set of cipher suites should be allowed. So for instance, maybe you would only like to allow elliptic curve cipher suites on your endpoint. You can do that through TLS configuration, as well as enabling or disabling certain TLS extensions, such as maximum fragment length negotiation. So that will be coming soon. But today, you are already able to configure your own custom domains and custom authorizers. So we'll take a little look at how this works. So let's say you had an existing IoT application, and you were hosting your own broker and using that to connect all your devices. And your own broker obviously has its own endpoint. So in this case, iot.examplecorp.com. And maybe you're even using MQTT username and password auth on this broker, which we'll get into in a second. But to start out, your application is scaling fine, you're adding more and more devices, and eventually you reach a point, maybe hundreds of thousands or millions of devices, where it's becoming harder and harder to maintain your own message broker and own backend for connecting the devices, and you'd like to migrate to a managed service, such as AWS IoT Core. But you don't want to have to reconfigure all of your devices just to swap out backend infrastructure. So you want to be able to keep the same fully qualified domain name that devices are connecting to and the same authentication and authorization scheme. So this is exactly what Configurable Endpoints is designed to do. And the first configuration is custom domains. So what you would do in order to register a custom domain is first go into AWS Certificate Manager, where you'd register your domain name and your associated server certificate. You would then receive an ARN, so an Amazon resource name, from AWS Certificate Manager, take that ARN and apply it to your domain configuration along with the exact same domain that you registered in ACM. At this point, then you could actually just set up regular DNS CNAME records to CNAME your custom domain to your AWS IoT Core endpoint, which would then in turn be translated to an IP address of our service. So when devices connect, all they need to do is send the custom domain that they're trying to reach. So in this case, iot.examplecorp.com. Send that in the SNI extension when they connect to IoT Core. And this enables us to go to ACM, retrieve the appropriate server certificate for that domain, and serve it to the device when you connect. So the other side of this is custom authentication. So you may have been familiar with the existing custom authentication feature that IoT Core has. When you use custom authentication in conjunction with configurable endpoints, you actually gain access to a bunch of additional functionality. And what we enable you to do now is enable custom authentication for MQTT connections. So previously, this was only available for HTTP publish or MQTT over secure WebSocket connections. And we also enable you a new wide variety of ways to pass your authentication tokens. So previously, you had to pass your token through a very specific Amazon-specific HTTP header. Now, if you're using HTTP publish or WebSockets connections, you can pass your tokens through any header that you would like or a query string parameter. And in the case that you're using MQTT over TLS or MQTT over secure WebSockets, you can also pass your credentials through the MQTT username and password field in the connect message. So we can take a little bit deeper look at how this works. So previously with custom authentication, the context that would be passed to your Lambda function that does the authentication was just the token. So in the event that we send your Lambda, it's just a JSON blob with the token in it, this blue section up here. Now, with the enhanced custom authorizers, we'll pass a huge amount of additional connection context for which you can make your authentication and authorization decision. So in addition to just the token, you'll also get all this really cool protocol data. So from the TLS layer, you'll be getting the SNI string that the device sent. If you're using WebSockets or HTTP publish, you'll also get context from the HTTP publish request or the HTTP upgrade request. And you'll get all the headers that the device was sending, as well as all the query string parameters. And in the case of MQTT over WebSockets or MQTT over TLS, you'll also get context from the MQTT connect message. So you'll be getting what was in the username and password fields, as well as the client ID. And you can use any or all of this data to make your authentication and authorization decisions. And all your Lambda has to do is return a valid IoT policy, as it did before. So the next feature I'd like to talk about gets into more about how you can pass device data to your backend application. And so we've released a new rules engine action known as the HTTP action. So what this does is enable you to make generic HTTP post requests to your own HTTP endpoints. Whereas previously, customers would have had to write their own Lambda if they wanted to interact with their own backend APIs, you can now do this directly through Rules Engine. So this saves you, number one, costs of having to use a separate AWS service, so you no longer have to pay for and manage your own Lambda functions to call your APIs, and also helps you avoid dealing with potential Lambda concurrency limits that you may hit if you have a large fleet of devices. And the final feature I'd like to talk about is actually a really, really big one. It's the Alexa voice service integration for AWS IoT Core. And what this is a brand new way of integrating the Alexa service into your devices that offloads all of the voice processing to the cloud and transmits all of the audio data over your existing AWS IoT Core MQTT connection. So we actually have a couple customers who are using this in production today. I don't know if you've seen, but in August, iDevices launched their Instinct line of smart home switches. And this is actually using the Alexa voice service integration for IoT Core. So we'll dive a little bit into how this works. There's three main components. There's first the client-side libraries. So you can get these directly as downloads from the Alexa website. Or you can purchase an integrated system on a chip from one of our hardware partners that incorporates all the hardware components that you would need as well as the software built in. And this does all of the audio encoding over MQTT to send the audio messages to the Alexa voice service. And those messages are actually transmitted over the second component, which is a dedicated set of MQTT topics for transmitting audio data directly to the Alexa voice service. And the Alexa voice service itself now has a new component called the Alexa IoT service, which serves as a virtual representation of your device in the cloud. And this is really where now all the audio processing, all the voice processing is done. Also, any audio streams that need to be sent back down to the device, whether that's just command messages or some kind of audio streaming, all that encoding is also now done in the cloud on the Alexa voice service. So that's it for the major features. I'd also like to recap some of the smaller features from earlier in this year that you may have missed. The first is a configurable rule limit. So we now have a self-serve way for customers to request limit increases on their account so that they can have more than 1,000 rules per account. We also, in May, enabled elliptic curve cipher suite support for your ATS endpoints. So previously, we only had support for RSA cipher suites. Now we also have all the ECC cipher suites that we support. Also, you may not have noticed, but if you're using IoT Core in the APAC regions, we've reduced the prices in Singapore, Sydney, and Tokyo to match those of Seoul, all at a 20% premium to US East 1. So all the APAC prices are now standardized and reduced. We also enabled support for a new quality of service 1 option on the rules engine republish action. So this is if you are receiving a message and you have a rule configured to republish that message, maybe with some modification on another topic, you can now configure that as a quality of service 1 publish. Previously, it was only available as quality of service 0. And finally, we've also expanded IoT Core into 8 new regions. So we've expanded a little bit earlier this year into Stockholm, Bahrain, Paris, Sao Paulo, Hong Kong, San Francisco, Montreal, and Ningxia. So with that, we're actually available in all current AWS commercial regions. So with that, I'd like to pass it over to Shane to talk a little bit about IoT Device Management and Device Defender.
All right, so first off, we're going to be talking about AWS IoT Device Management. So IoT Device Management enables customers to manage their devices at scale. And it comprises of 4 main components. So there is bulk things provisioning, there's fleet indexing and search, jobs, and we've just added secure tunneling. So first, let's go over bulk registration. So in the general device provisioning process, there are 2 steps. The first step is to be able to generate unique certificates for your device. The second step is to be able to register those certificates and associate them with a thing on AWS IoT Core. As Jared previously mentioned, the fleet provisioning service provides you the end-to-end capability of generating unique certificates as well as registering them on AWS IoT Core. Bulk registration is really focused on customers who already have unique certificates generated and just want to be able to register them on AWS IoT Core. Secondly, there's fleet indexing and search. So with fleet indexing and search, customers can index their device metadata, such as data that they store on registry, device shadow, or connectivity. And they can query that index data or get aggregate level statistics on that data. And we'll get into more detail what that means to get aggregate level statistics in a later slide. With jobs, customers can target, roll out, and manage batch over-the-air actions on individual or groups of devices. And then finally, secure tunneling, where we now provide you the capability to access individual devices remotely, specifically for troubleshooting use cases, and those that, and we've seen that this is specifically used for devices that are on restricted networks. So for 2019, AWS Device Management really has focused on managing your device fleets at scale. So generally what that means is customers want to be able to understand what's going on with their devices, be able to organize it in a way that's actionable, and then to be able to take action on individual or groups of those devices. So let's take, for example, a customer who has a fleet of TVs. And these TVs are sold to end users around the world. They may want to be able to understand what's going on with those device fleets. And that's how fleet indexing and search can help them. They can index that device metadata and then be able to query on that data to understand it better. Then they want to maybe organize it in something more actionable. So they may start organizing it with model types and firmware versions and different configurations, and even by location or region. And then finally, they want to be able to take action on those devices. And they can utilize jobs or secure tunneling to do that. Jobs will help you on both individual or both groups of devices, and secure tunneling will help you on individual devices. For 2019, we focused on a few major releases. First, it was aggregation queries. Secondly, secure tunneling. And then finally, we've added 8 new AWS regions similar to AWS IoT Core. So now we're in 21 AWS regions globally. So let's dive a little bit deeper into aggregation queries first. So aggregation queries is an enhancement to fleet indexing and search. And what we provided are fleet level metrics for customers to be able to alert and to set alerting and monitoring. And from there, you can basically define simple statistics such as count, average, min, mean, max, percentile support, or even getting some kind of unique count. Let's go through a few examples. So the first example is a customer might want to understand what is the number of devices that are currently on version 1.1. So the way the customer would be able to do this is they would first store their version firmware on device shadow. They would then be able to index that data using fleet indexing and search. Finally, they could set up a query to see which devices were on what version. And then afterwards, they could use the Get Statistics API in order to get aggregate level statistics. So in this case, they would be able to see that there are 3 devices that are currently on version 1.1. The next thing is maybe they also want to understand what the mean time since the last failure was. So a customer could then do the same thing, where they would utilize device shadow to store that last failure duration for each device. They could then index that data and set up a query to be able to see how each device is performing. And then finally, they could get the mean time since that last failure. And then finally, maybe a customer also wants to understand what's that bottom 10% of battery life or battery level right now of their existing device fleet. Generally, this might be used in a specific property or some kind of thing, devices on a specific property or wherever. And similarly, they could utilize device shadow in order to store that battery level data. They could then set up a query to see where those, how each individual device is performing. And then they could get aggregate level statistics to kind of showcase what that bottom 10 percentile is so that they could address this issue. So as you can see with aggregation queries, customers can utilize these aggregate level metrics in order to start setting alerting, monitoring for anomalies, or potentially even setting actionable automation or augmentation to other types of, to use like jobs or some other kind of control mechanism. The second thing we're going to go deeper into is secure tunneling. So secure tunneling is a mechanism in which a source and destination device are connected via a tunneling service. And it opens up a logical pathway by which customers can utilize in order to start troubleshooting their devices. So this is generally used for devices that exist behind, unrestricted networks or behind kind of corporate firewalls. And generally what we've seen is that secure tunneling is used for customers who are wanting to diagnose a device issue, be able to deploy a fix, and then from there be able to validate that the device is working properly. So there are some prerequisites to using secure tunneling. So for example, each device is required to install a local proxy on both the source and the destination device. Secondly, generally there's a recommendation that there's a device agent on the destination and local device to be able to listen to MQTT reserved topics. And finally, there's an interface required with the client SDK, which enables customers to be able to talk to the tunneling service via the management APIs. And this is where they can manage the tunnel lifecycle, such as opening or closing the tunnels. So for this particular scenario, let's pretend that there's a tech support person that's actually utilizing this computer. That person could initiate this tunneling service by opening a tunnel via the client SDK. From there, the tunnel service would create two unique access tokens, and be able to pass that down to each source and destination device. Each of these source and destination devices would receive that token via the device agent, and that device agent would then boot up the local proxy. The local proxy would then initiate an outbound connection back to the tunneling service, and that tunneling service would then broker that connection. After this connection is established, customers can now troubleshoot. So if they would like to be able to, they could utilize remote shell type stuff such as SSH or some kind of SCP commands. They could utilize remote desktop or some kind of virtual network computing. Or finally, they may have some custom remote management application. But generally, they could deploy this through the tunnel. And then finally, once they're done with that troubleshooting use case, they could then actually close that tunnel. All right, so next up, we're going to go through a quick video demo here on exactly how the secure tunneling works. And this is going to be done by Martin, one of our solutions architects. And he's going to go over 4 things. So the first thing is going to be, how do you create a device on AWS IoT Core? Secondly, it's how do you actually set up all those prerequisites needed to get started with secure tunneling? Third, we're going to go through the open tunnel. And then finally, we're going to actually initiate an SSH session. So let's watch.
Today we will be doing a walkthrough of the new AWS IoT Secure Tunneling Service. Before we begin, we'll need to ensure that we have a thing in the AWS IoT Thing Registry. This is to support the Managed Token Delivery feature that we'll be walking through a bit later in this demo. So to get started, we're going to onboard a device from the Onboard tab in the AWS IoT console. We'll select Linux OS X as our platform and Python as the device SDK. We'll give our thing a name, in this case RBPi, and go ahead and download the connection kit. Now, this connection kit includes several files we don't need. The only ones we need to keep are the certificate and the private key. The others we can delete. However, we do need to add some additional files, including the actual Python script that will be listening on the AWS IoT broker for new messages and executing the local proxy. We'll add the local proxy as well as the Amazon root CA to this folder, which we'll be zipping up and sending to the device later. Let me show you a bit about this Python code to help you understand what's going on here. This is the basic pub sub example from the Python SDK website. We've simply stripped it down and made a couple of modifications. It simply subscribes to a special reserved topic specifically designed for secure tunneling. This is per thing name. So we're listening to a thing name specific topic. And once we receive a message on this topic, we'll be initializing the local proxy using the binary that was built specifically for Raspberry Pi from our reference code. We'll be passing into this proxy the client access token from the message, and we're using localhost and port 22 hard-coded. However, in practice, this could be any host and port configuration file. So once we're all done, you'll see we have a thing in the thing registry. We also will have a certificate attached to our thing, and we'll have a policy attached to the certificate. Now, our default policy that we normally create is actually not suitable for tunneling, so I pre-created this policy so that it would automatically attach to our thing and certificate. Let me show you what this policy looks like. It's a minimalist policy that only allows receiving and subscribing on the special tunneling topic, as well as connection using the thing name's client ID as a client ID. Note the use of policy variables here to make this policy simpler to use. So with that all set, we're ready to start configuring the device. On the bottom right here, you'll see the window where I've SSH'd directly into my Raspberry Pi on my local network. We'll use this to monitor the local proxy and initialize the local proxy. On the left, we have a shell window which we'll be using to run the local proxy on my local laptop. And we'll then be using the top window to connect to this local proxy and pass through to the Raspberry Pi. So it'll start with our top window SSHing, coming through to the bottom left window of our local proxy, which will then connect over to AWS IoT and communicate to our Raspberry Pi. So to get started, let's go ahead and zip up that connect package. Okay, all set. So now we need to get this connect package onto the Raspberry Pi. Since for this demo I'm on the local network, I could simply just SCP the code over. Now note that there's nothing on the device right now. I just did an ls and there are no files on my current directory. So I'm going to go ahead and SCP that over to my home directory on the Raspberry Pi. And there you go. So I'll go ahead and unzip that. And go ahead and initialize that script I just showed you to start my listener on the special topic to listen to AWS IoT for the tunneling notification. Now, the two parameters I need to pass into this script are my AWS IoT endpoint and the thing name that I just created. And there you go. Now you can see that I have an MQTT listener listening for messages. So now I'm going to come to the left window here and open a new tunnel using the CLI open tunnel command. I also need to pass in two parameters to this command, the thing name, as well as which services I want to use. As I previously mentioned, you could actually specify a number of different services and then use a configuration file to map those. And then finally, I'm only going to extract the source access token out of this command for use later. And there you go. You see that when I ran this command, it passed the message to my Raspberry Pi, which received it and then opened up the proxy and established a WebSockets connection up to AWS IoT. So now I need to come back to my local machine and start the local proxy on my local machine. Again, I'm going to use the source token that I just saved into the environment variable, specify the region, and then which port I want to use for my local machine to connect on my local machine to the proxy. So in this case, I'll just specify 8000. And there you go. You see the WebSockets connection was successfully opened. So now I have both my local machine and the device using WebSockets connecting up to AWS IoT, and I am ready to SSH onto my device. I simply type in my Raspberry Pi's username and password, specify port 8000, and there you go. I have now SSH'd to my Raspberry Pi over the internet through AWS IoT through a firewall. And you can see all my files here that I just copied over. So with that, I thank you for taking the time to watch our demo, and I'm excited to see what kind of use cases our customers will use their service for. Thank you.
All right, so to recap, as you can see, Martin's demo is able to show how we actually, all the prerequisites necessary to set up a secure tunnel, how to actually open a tunnel, and then how to initiate an SSH session to be able to remote troubleshoot, specifically for devices that are behind restricted firewalls. And this is really useful for a lot of these customers that have that use case. All right. So Now I want to take it back a little bit to the overall goal of device management. And that goal was really to enable customers to be able to manage their device fleets at scale. So I thought best to walk through an example use case here. So let's just say there's a commercial property owner with 100 office locations in Paris. And they have currently an energy management IoT platform that's monitoring devices such as smart lights, thermostats, and motion sensors. And really the goal of this energy management platform is to monitor energy consumption and to be able to reduce energy costs. So with this, let's pretend now that there's one of those office locations currently is actually having an issue and it's consuming a lot more energy than all other office locations. So how would we go about this? So first, a customer would want to understand this problem. So they could utilize fleet indexing and search in order to do this. And fleet indexing and search, they could index that device metadata, such as their shadow and their registry data, and then they can go and start looking for all various different devices. And in this case, these are thermostat devices that are located in Paris. Secondly, they might want to be able to organize those devices into something that's more actionable. So they would utilize aggregation queries in order to get aggregate level statistics, such as maybe finding the average temperature range for thermostats that are in Paris. And you could set up that using that query there. Afterwards, a customer might want to understand maybe the anomalies. So to be able to further organize something into something actionable, they could utilize aggregation queries and specifically the get percentiles API in order to find thermostats with current temperatures that are in the 95th percentile. So in this case, maybe after investigating, they find that 2 thermostats in Office 2 are showing temperatures that are exceeding that 95th percentile. So what would they want to do now? Well, the next step is they would really want to take action. And that's where secure tunneling comes in place. And first, they would be able to use secure tunneling to access the individual devices in each office to be able to troubleshoot. So for example, they may want to look at a good device in office number 1 and one of the misbehaving devices in office number 2. And they might want to be able to compare. And they could use secure tunneling to access device logs. They could configuration files, custom applications that maybe only run on the device. And maybe they were able to figure out that currently these devices that are in office number 2 are actually on firmware version 1.1. And they really need to be updated to version 1.2. So right now, they could actually take 2 approaches. So the first approach could be that they could troubleshoot this individual device, device by device, using secure tunneling. And this would work perfectly fine. The alternative approach is that they could utilize dynamic groups and continuous jobs. So let's go over first what dynamic groups is. So dynamic groups is a query-defined group that enables customers to be able to utilize similar fleet indexing and search type queries in order to create these groups that dynamically update based on that query. So for example, I could set up a query that says, I want to look for all thermostat devices that have version 1.1 that are in Paris and that have some kind of, that are currently connected. And from there, I want to be able to have them added to that group dynamically, and any new devices that meet that criteria will be added to that group as well. From there, they could set that up to work with continuous jobs. Now, continuous jobs is, as we recall, jobs is really about enabling customers to target, roll out, and manage remote actions against individual or groups of devices. And continuous jobs enables you to continuously monitor these dynamic groups as new devices get added to that group. So a customer could set this mechanism up to have a continuous job that would update of their version 1.1 to version 1.2. So all of the devices that meet that criteria of the dynamic group that get added in will then have a job executed against them to update the firmware version from 1.1 to 1.2. After which, those devices could then report via shadow that their version is now on 1.2, and based on that, they would automatically be delisted from the dynamic group. So this is powerful because, imagine this property owner is now launching another property, office location number 101, 102, right? And any of these new thermostats that come online that are on version 1.1 will automatically be added to this dynamic group and then updated to the appropriate version. So as you can see, with the device management suite, we've provided the capability for customers to really manage their fleets at scale, being able to understand their problems, organize it in a way that's actionable, and then to be able to take action on that. Now, next, let's turn our attention to AWS IoT Device Defender. So AWS IoT Device Defender enables customers to continuously monitor their fleets for security. And we provide two components. There's detect and there's audit. So detect enables customers to continuously monitor their fleets based on metrics that they collect and be able to alert on any type of anomaly behaviors. And audit enables you to set up an audit on AWS IoT resource configurations and then be able to mitigate issues based on whatever violations happen in the findings. So a general workflow would be for Device Defender is that a customer would come in and they would set up an audit on AWS IoT resource configurations. And these could be anything from policies, permissions, they could do it on account settings, and they could do it on certificates, and they would set that all up. Secondly, they would set up continuous monitoring for device behaviors and being able to identify any types of anomalies. And they would do this via detect. They would set up a security profile in detect and be able to do that. After they set up their audit and their detect, they could then set up alerting. So they could, and this alerting could be done via AWS IoT Console, SNS, or CloudWatch. And then finally, from any of the alerts that they get, from their audit findings or from any types of detection alerts, they could then investigate and then mitigate those issues when necessary. So let's first look deeper a little bit in audit. So audit is, customers again can actually set up audits in order to monitor their resource configurations. And specifically, they can set up these audits based on AWS IoT security best practices. Some of the types of audits that they might set up is looking for expired or revoked certificates. Other things would be maybe overly permissive policies. So for example, any types of device access that might be a little bit too intrusive. Other types of things would be device connections that have maybe shared identities. So for example, if there's everything that's in this facility here have the same identities, they may want to be able to sort of revoke existing certificates and generate unique certificates. And then finally, they might also want to have audits set up for any types of user settings that are updated, such as if logging is set up or enabled. Now, secondly, if we dive a little bit deeper into detect, so customers again can utilize detect in order to continuously monitor and be alerted on any types of anomalies that go on. So the way that detect works is a customer first sets up a security profile, and they can monitor both device side or cloud side metrics. And specifically with detect, customers can monitor things like bandwidth, connection, source destination IPs, any types of authorization failures. And from there, they can be alerted on any types of relative thresholding issues or any types of percentile-based outliers. So as you can see sorry. All right. And basically, I think this kind of concludes our seminar based on device management and Device Defender. If you're really interested in learning more about Device Defender and some of the more securely related features, you can visit IoT213-R, and it's designing secure IoT solutions from edge to cloud, where we look at AWS IoT security best practices, as well as how to design secure solutions. Additionally, if you're interested in learning more about IoT and potentially getting trained or certified, here's some information here on how AWS can help. This concludes our presentation, and thank you for listening.